Okay. Which problem is it? Okay. And
I follow the steps in the textbook example, but it looks like it's too complicated to finish. So I don't know if I'm on the right track or not.
okay. So, all right. So this is chapter 5, number 12. So the problem is u. Okay. Ut minus uxx minus 9u over 4 is 0. Okay, and then we have, this is on 0 pi. Okay, u0 pi is 0 and du dx, or so 0t. So Dirichlet at one end, Neumann at the other end. And then we have initial condition, 3x over 2 and 9x over 2. Okay, so okay. So separation of variables, what's going to happen is somewhat different ODEs. So if we use the same separation of variables assumption, u is equal to big X of x, big T of t. So we get xt prime minus x double prime t minus 9xt over 4 equals 0. And then you divide by xt, so you get t prime over t. And I'm going to move everything else over to the other side, so you get x double prime over x plus 9/4. And all of this is equal to the separation constant minus lambda. So what happens in this case is it's a similar, okay, so you have t prime plus lambda t is 0. So that ODE for time doesn't change at all. And then you have x double prime plus that. So what happens is the eigenvalues are all shifted. So you're going to get to similar kinds of eigenfunctions as you would as you would normally get. And in fact, what's going to happen is because your initial data is in a convenient form, that's going to make it easier to get the coefficients involved. Now, okay. But the thing to keep in mind is when you're trying to solve this kind of ODE, so recall the original form, x prime, I'm going to change the letter a little bit just to distinguish. X double prime plus mu x equals 0. Only has solutions to satisfy. Let's make sure I'm actually capturing a board here. Sorry, for those of you watching at home. Okay, satisfy the boundary conditions. Under certain conditions on mu. So really, the thing to make sure of that you have a solution fully described is Because normally you're checking mu is negative, equals 0, positive. And for most boundary conditions, what we find is that mu cannot be negative. It should never be like positive in some cases, like for Dirichlet boundary conditions, or for Neumann boundary conditions, mu should be at least non-negative. It's still allowed to be 0. So it'd be a good idea to check this because we've seen in the notes, it's also or the textbook, we have general solutions for all three cases: mu positive, negative, and equal to 0. Where you have like quotient sinh for the negative case, and a linear function for the 0 case, and then a sine or cosine for the positive case. Now, what about these boundary conditions? Which kind of solutions will satisfy them? And therefore, so suppose what you conclude based on these boundary conditions is that mu has to be positive. So that would mean that lambda has to be greater than minus 9/4, for instance. So all your eigenvalues are going to shift because of this 9/4 term being added here. So it shifts the eigenvalues but not the eigenfunctions. The eigenfunctions come from the basically come just from the boundary conditions. The eigenvalues are determined by the PDE itself. Okay. So what you're going to do is you're still going to have, just like in other problems, some sort of eigenfunction expansion where you choose a coefficient to satisfy the initial data. Now, what's going to be quite convenient is your eigenfunctions are actually going to be of this form. So if your initial data is a linear combination of the eigenfunctions you actually get, then the coefficients in your initial data are the coefficients in your solution too. So you're going to see these functions in your solution along with exponentials that come from this. Now, so I want to point out one thing that can happen for this particular PDE, because this coefficient here, the minus 9/4, that because it's negative, this term allows some exponential growth in the solution. And again, because it's negative. Now, here, the minus in front of the uxx on this side is going to lead to exponential decay, the same kind of decay that you always see in the heat equation. But this is called a reaction term. So when you have no derivative, so two derivatives is diffusion, one derivative is advection, no derivatives, that's a reaction term. And depending on the sign of the coefficient, you could have exponential growth or decay. Now, I want to emphasize, though, whether you actually get exponential growth in your solution depends on the initial data that you get. Okay. I'm not sure if this answers your question about how you approach this problem.
I use the method on page 121.
Okay.
121 and 122.
Okay. Okay, so you made a change of variable. Okay.
When I plug into the boundary conditions, because of the
Yeah.
first order differentiation, it's not like in the textbook. So
Mm.
give me a very lengthy documentation.
Okay. All right. So what he's talking about is for a problem like this where you have this diffusion term and a reaction term, that the solution. Okay. Yeah. It's separated a little differently. So it's still separation of variables, but you have a function of x that a cosine that depends on t and x. So I'll refer you to page 122 is where, 121, 122, where the change of variable actually occurs that transforms into basically a heat equation. Okay. And actually, what boundary conditions? Oh, this is boundary condition at infinity. Okay, so you could still try using the same, same change of variable. It's just that you're going to have more ordinary boundary conditions to solve, boundary conditions to apply. Okay. Now, in that problem, the coefficient was actually it was a negative coefficient, so that's why it's an exponential. Okay. Yeah, so one of the difficulties, or I guess one of the discrepancies between that problem in the book and this problem is when you get down to your ODE, we don't know what lambda is yet. We know based on the boundary conditions that this, let's see. I believe this whole term at least has to be positive. And that leads to trigonometric functions for your eigenfunctions. Whereas in the problem in the book, you had this ODE had a positive coefficient here and a minus sign that led to exponential functions as your solution. So really, the only thing you could take from that problem to use in this one is the actual change of variable is still valid. So in this case, u of xt is x of x times cosine kx minus omega t. That so something like this is actually, let's see what they got for their time solution. Oh.
I use this only one term, so maybe it's not good enough. Maybe I should use more terms.
Well, one of my concerns about this is since there are only time dependencies in terms of a cosine. Okay, so when I try separation of variables, okay. Cosine phi term. Yeah, because that solution is not going to have any exponential decay. Which is interesting because there's still a diffusive term. Okay, because if you try separation of variables on this, well, it depends on what you choose for your separation constant. Okay.
Anyway, let me try your method first.
Yeah, because so this is what the book tried in case you want to try it, but I feel like more flexibility is needed, and so just sticking with regular separation variables where x and t are allowed to be anything, and just solve the ODEs that you get. Yeah. Okay. Other homework questions? I know it was a silly question for me to ask, but what did I make his homework do? Okay. Yeah, because I have been getting a few other questions on it, not many, so okay, good to know. All right. Fortunately, I did not have any particular. Sorry, but I'll change this again. So, okay. Actually, I seem to recall when I taught 417, 517 that something similar to this came up. As a change of variable, you can make it transform this kind of problem into a heat equation. All right. So the thing to do is verify for this general ODE based on the boundary conditions that you have. So 0 on the boundary, and then a 0 derivative, so 0 at the left endpoint and a 0 derivative at the right endpoint. Can you have eigenvalues that are positive, negative, or 0? So I can tell you right now, for this kind of ODE, 0 will not work as an eigenvalue. And the reason is, if mu is 0, your solution is a linear function. You cannot have a linear function that is 0 at one end and a 0 derivative at the other end unless the whole thing is 0. So, so we know that this case is out. Now, mu being positive is definitely okay, because that's where it gives you your trig functions. And there are sine functions that will work for these boundary conditions. It's worth checking if you have like Koch or Cinch, some linear combination of those. Is it possible to have a combination of Koch and Cinch that satisfies these boundary conditions? And if not, then this case is also out, and you're only going to have sine functions as your eigenfunctions. But then you take it into account down here, and you see, okay, now you're going to have a shift in the eigenvalues because of that plus 9/4. Okay. You have a question on the homework? All right. Wasn't sure how much sure if I had enough notes for today anyway. So actually having all this discussion on the homework is a good thing. Okay. Oh, I need my charging cord. I forgot to bring that in here. Okay. Recording was interrupted. I'm not sure how much was lost. So I'm going to do a quick recap of this board and then carry on from there. Hopefully nothing else goes wrong. So where I left off last time, orthonormal expansions, F is a combination of these basis functions, the phis. They're orthonormal if the inner product with them is equal to 0 if they're different, and 1 if they're the same. Using this notation, Kronecker delta, as a shorthand to express that on one symbol. That makes the coefficients easy to compute. Each of these coefficients, a sub n, is just the inner product of each basis function with the function that you're trying to expand. And that's written here as an integral for a general inner product. So as an example, sine nx, these basis functions on the interval 0 to pi are found to be orthogonal. The inner product of different ones is 0. And if the inner product of each of these basis functions with itself is not 1, it's pi over 2. That means they are orthogonal because of these inner products being 0. Because the inner products themselves are not 1, they are not orthonormal. And the way you can see that, this is in the notes in detail, but it's a product of some identities, it's trig identities, that you can use to evaluate that integral. Okay. Sorry about that with the recording. I'm not sure what really happened or how much was missed. But at least everything on the board is being caught. Okay, so now I want to try to get orthonormal functions from these orthogonal ones that we have. Before we run out of time altogether. Okay. We normalize. So the inner product of sine nx with itself, what we found is that is, now keep in mind, that's the same as the norm of sine x squared, and that is equal to pi over 2. So the norm of each one of these is the square root of pi over 2. So that means a set of all functions where we take sine nx and we divide by its norm, so square root of 2 over pi. These functions are orthonormal. Okay. Okay. So we can express function f of x as an expansion of these functions, and then we have square root of 2 over pi sine nx, and each coefficient is the inner product of one of these basis functions with f of x. So that's just going to be the integral, so square root of 2 over pi times the integral of f of x sine nx. Okay. And this is called a Fourier sine series. Now here we're using the interval 0 to pi. We could define a sine series on any interval, just rescale things as needed. Funny thing is, when you see these Fourier series written, you can see them written so many different ways in different books or websites because of what interval they deal with or what scaling constants they use. Different sources might take this, because notice you have a square root of 2 over pi here in a series, and another square root of 2 over pi here in the integral. So, so an alternate way to write it would be f of x is sum of an sine nx with no scaling constant, and then an is 2 over pi integral from 0 to pi of the same integrand. So the only difference between this way of writing it and this way of writing it is you have 2 over pi in total, and here in the second form I put it all in one place. Here I made it more symmetric by distributing it square root of 2 over pi here in the expansion, the other square root of 2 over pi in the integral. So you could, that's why I say Fourier series are written so many different ways in different sources because of how they place the scaling factors. So that's just something to keep in mind if you look at other sources. But they're all equivalent. It's just a matter of how these scaling factors are distributed. Okay. Any questions about this normalization and orthonormal basis expansion? All right. Okay. Now, a generalized Fourier expansion so we usually functions that may not be sines or cosines at all. So I'm going to use Fn hat to refer to the coefficients of the expansion. And then the phi sub n are the basis functions, whatever they happen to be. So these are some orthonormal basis. For whatever vector space you're dealing with. And therefore, their coefficients, again, are the inner product of each basis function with f. Okay. And these are called Fourier coefficients. Okay. So it may not be a Fourier series in the usual sense, but a lot of the same concepts apply. That's why we still refer to it as using a Fourier name. Okay. Now, this is an infinite expansion now. Suppose I truncate it at some point. So I'm going to let f sub n be the first capital N terms. So I just cut off the expansion after that point. So this f sub n is called the orthogonal projection of f onto a subspace of a space spanned by all the basis functions. So we take a span of your first n basis functions. Okay. The notional projection is very important because, especially in, for instance, numerical analysis, what you're doing is you're taking some function from a vector space that is infinite dimensional, and you are projecting it onto some finite dimensional subspace. Because what are you often doing? You're representing your function by its values at certain grid points. So right away, because you have a finite number of values, you're restricting your function to a finite dimensional subspace. And you may be using some finite dimensional subspace like sine x, sine 2x, sine 3x up to sine nx to represent your function. Okay. Now, so one property of your orthogonal projection is very important is it is the best approximation this is actually, so the norm of the error in your orthogonal projection, which is actually equal to the norm of f itself squared, and then you're subtracting off the absolute values of the coefficients that you've kept. Okay. So subtracting off all of that, this error is less than or equal to, I'm going to call this subspace, I'll call it V sub capital N. So this is the subspace of all of these first n basis functions. So this error is less than or equal to the error you get by approximating f by any other function in V sub n. So in other words, if you're trying to find the one function in this subspace that approximates f as well as possible, this is your best approximation. So now, another consequence of that is that the error, f minus fn, is orthogonal to every function in this subspace. All right. Now, I can actually convince you that this is the best approximation using a simpler example from a much simpler vector space, R2. So suppose you have a vector in the plane, and you want to approximate this by a vector going in this direction. So I have a vector in a two-dimensional space. I want to approximate it by a certain vector in this one-dimensional space, a vector on this line. Does anyone remember, if I want to approximate this vector by something on this line, how do I do that? How do I, pictorially, how do I get that approximation? I want to approximate this vector by a vector along this line. So basically projecting this vector onto this one.
Projection. There was something linear.
Dot product.
You do use a dot product, so algebraically that's how you'd work it out. Can anyone tell me geometrically how you'd work it out? Just using the picture. What?
Perpendicular.
Perpendicular, yeah. You draw a perpendicular. Oops. So this approximation, this is the best approximation because the error is this gap here that is orthogonal to the subspace that you're using for the approximation. So this is a very universal concept of orthogonal projection of some vector onto a subspace. The error is orthogonal to the subspace onto which you're projecting. So that's true for ordinary vectors in Rn. It's true in function spaces, any such vector space, where you could any inner product space whatsoever. This applies. Okay. All right. Now, the reason I wrote out this error in this form. Now, you can actually figure out that this is the error from here using properties of inner products and norms to arrive at this. But the thing is, this is a norm. Therefore, it's greater or equal to 0. What that means, therefore, is this whole expression under the square root sign is also greater than or equal to 0. So I get a very important result if I just take that into account. Not so good. Okay. 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 So what we get from that is what's called Bessel's inequality. Which says that the sum of the absolute values of squared of all the Fourier, generalized Fourier coefficients of a function f is less than or equal to the norm of f squared. So all I do is I take what was under the square root sign on a previous board, and I just let capital N go to infinity. Because it's true for any finite n. Okay. Now, if the underlying vector space that you're working in is complete, and what that would mean, the consequence of that is these orthonormal functions form a basis for us. In other words, you're able to describe all functions in the vector space using these orthonormal basis functions. In other words, what you have is a Hilbert space. Then, Bessel's inequality becomes equality. And this is called Parseval's identity. Okay. So in fact, what this is saying is you can compute the norm of your function in two different ways. In physical space, you're taking the integral of a function of x, or you're taking the sum squares of all the Fourier coefficients. You're working in frequency space. So taking the norm in either physical space or frequency space gives you the exact same result. So this is what Parseval's identity gives us.
So if the vector space is complete, there is no error? Or?
Essentially, yes. Except like on a set of measure 0. And this is something I'll get to later where you can have deviation, like for instance, suppose your function is discontinuous, but your basis functions, like your sine and x or something like those are all continuous. You could have a discrepancy at isolated points. So just a set of measure 0, but that's it. Otherwise, yes, the error is 0.
Because that equals means that square root guy is 0, which means 0 less than equal means the error.
Yeah.
Right.
Okay. Now, what we have here is, what we're saying is this infinite series converges. But if an infinite series converges, that means that the individual terms, have to go to 0. So an immediate consequence of this, and actually this would also be true for Bessel's inequality also, because in either case, this series converges. It doesn't matter whether it's equal to this or it's bounded by this. We have that the limit, as n goes to infinity, of each coefficient, because this is fn hat, is 0. And this is called the Riemann-Lebesgue lemma. Interesting name because Riemann and Lebesgue are responsible for two main types of integrals. You're familiar with a Riemann integral from calculus. So there's also the Lebesgue integral, which if any of you take 641 analysis next time, I believe you will learn about the Lebesgue integral. It's more general. Or there are certain functions that are Lebesgue integrable but are not Riemann integrable.
Yeah, Dr. Ding is like sort of, it's got to be allowed. It can be discontinuous, at a finite set or something.
Yeah.
Yeah.
So I guess he can tell you all about that if you take that class. So yeah, so we have it, the coefficients of the expansion decay to 0 as you go to infinity. Okay. Now, if this orthogonal projection actually converges to your function f, which is going to happen if you have completeness. The verbiage for this is that Fn converges to the mean, or sorry, converges in the mean to f. All right, and we say converges in the mean instead of simply saying converges because converges implies that you have point-wise convergence at every single point. And as I just mentioned, that actually doesn't happen. It does except at certain isolated points. There are exceptions for rule, but so we have a slightly weaker form of convergence that we're short of, convergence to the mean. And what we'll see is it all depends on how your function behaves. If your function is, for instance, continuously differentiable, then we actually have straight-out convergence. Point-wise, everything. But when you have discontinuities, that muddies the water a little bit. Okay. See how much more I can cover. All right. Well, this next example I definitely want to do. I think it'll be helpful for upcoming problems. Okay. So as an example, I'm going to let fx equal x at interval minus pi to pi. Okay. And I want to expand, so considering my vector space, 2 pi periodic functions. Okay. Now the thing is, f of x equals x, if you think of it as a 2 pi periodic function, it is not continuous. Because if you take f of x equals x and minus pi to pi, and you do a 2 pi periodic extension, you're going to introduce a discontinuity. So you have a situation like this, where here's f of x equals x from minus pi to pi, and then you extend it, so you're going to get something like this. So every 2 pi units, there's going to be discontinuity. Okay, so the expansion we want is this form. It accounts for all different sines and cosines of the appropriate frequencies. So the a's, ANs are the coefficients of cosines, and the BNs are coefficients of sines. Okay. Now, when it comes to even and odd functions, cosines are even, sines are odd. What about x? X is an odd function. So what's going to happen is, so it turns out that so a sub n is, something seems here. All right, this is for 1, 2, etc. And A0 is just the integral of minus pi to pi is f of x dx divided by 2 pi in this case. Now, f is odd, and cosine nx, or 1 in this case, are even. So it turns out that integral of an odd function over a symmetric interval is 0. So we're going to get 0 for all of those. Okay. So it's really just to b ends that are left. So b sub n has a similar definition of a sub n. So it's 1 over pi. That'll be f of x sine nx, or x sine x dx. Well, 1 over pi comes about because so it's something like this came up before, but the integral from 0 to L of sine squared nx dx is L over 2. In this case, L is equal to 2 pi. So we're dividing by the inner product of each of these functions, cosine and sine x or 1. We're dividing by the inner products of those functions with themselves. So this is the same as the inner product of sine nx with f over inner product of sine nx with itself. So this is where these scaling factors are coming from. So we keep in mind all these functions are orthogonal. We could write them as orthonormal, but that's going to introduce a bunch of annoying square roots. So I'm not bothering to do that. So we're just sticking with this formula. So this is equal to L over 2, which in this case is pi. So that's where that's coming from. Okay. All right, I think I have just enough time to finish this.
Is where the 1 over pi is coming from?
Yes. Yeah. Okay. If I wanted this orthonormal, I would have scaled all the cosine nx and sine x's by 1 over square root of pi, and then had a 1 over square root of pi in front of the integral. But why have all those square roots when it's not necessary? So we're using orthogonality, not orthonormality. Okay. Now, this integral has to be worked out using what?
Parts.
Integration by parts. So what you get is 1 over pi, and we get, so this is your u, and this is your dv. So your v is going to be, whoops, this is sine nx, not x. Sorry about that. So v is going to be minus cosine nx over n. So what you're going to get is minus x cosine nx over n, with limits minus pi and pi, plus 1 over n integral minus pi to pi of v du. So we're going to get cosine nx. All right. Now, when you evaluate this integral, cosine nx from minus pi to pi, even though it's an even function, you're actually going to get 0. So, because what's the integral of this? It's going to be sine nx over n, and you plug in the limits, and you're going to get 0. So your only contribution is going to come from this. So when you simplify everything, and I won't do everything here, but it's in the notes. So you have minus 2 over n cosine n pi x with limits minus pi and pi. Okay. Right. Yeah. So what you end up with is, what is cosine? Okay.
Well, cosine is even, so can you not have like 2 times from 0 to pi?
Oh, this integral?
No, that goes to 0.
Yeah.
Oh, now you're evaluating that.
Yeah, but plugging in the limits for,
Right.
okay. Actually, well, something looks strange in my notes, so I'm going to go off script here. Okay, so I have minus pi cosine n pi over pi n from the upper limit. And then for the lower limit, I have a minus, and then I have, but I also have another minus because I'm taking a lower limit, which could be a plus. Then I have minus pi cosine minus n pi over pi n. And what happens is cosine, because it's an even function, cosine minus n pi is the same as cosine of n pi. So I can erase that minus. The two terms add together, and you get minus 2 cosine n pi over n. Okay, so actually there's a slight mistake in my notes. And that's what kind of threw me off and led me to do it this way. So I will fix that later. Okay. So at least the final formula that I have in my notes is still correct. So cosine n pi, what does that equal to?
Or n equals 1 and everything. That equals 1.
Wait, no.
What?
Yeah, 1.
Yeah, 1 negative, well, depending on n. So if it's
Even,
even, it's 1, and if it's odd, it's minus 1. We also have a minus sitting here. So we actually get 2 over n times minus 1 to the n plus 1. Okay, so now we can go ahead. So those are our coefficients, our bn's. So now we can say that our series for x is 2 sum n equals 1 to infinity of minus 1 to the n plus 1 over n times sine nx. Okay. Now it seems strange that we can express this function x that has a discontinuity in this 2 pi periodic extension as an infinite sum of functions that are plainly continuous. And here's what happens if you actually go ahead and do that. So I'm going to add to my picture here. So here's the actual function I'm trying to approximate. And as you form your series, what you get is something like this, where you have oscillations near the, so away from the discontinuity of minus pi and pi, you do get convergence. But as you approach the endpoints, minus pi and pi, you get these troublesome oscillations, and when the function jumps down, more oscillations here that go away as you move away from discontinuity. So this is how your 2 pi periodic extension, and therefore your Fourier sine series, behaves. So these troublesome oscillations, as you add more and more terms to your series, the oscillations are lessened somewhat, but they don't go away entirely. And you have to stop your series at some point, obviously. So eventually they would all go away, but you can't do this infinitely. So this is a troublesome phenomenon called Gibbs phenomenon, after the mathematician who discovered it. Okay. You get oscillations near discontinuities. in a 2 pi periodic extension. I put a 2 pi parentheses because we can do this on any interval, whatever periodicity you have. If you have discontinuities, you're going to get this Gibbs phenomenon. If a function itself had a discontinuity in the interior of the interval, so not related to the 2 pi periodic extension, you will again get these high frequency oscillations. They're awful. And this is one drawback of Fourier series. It's not good for approximating discontinuous coefficients. And in fact, if you chose a lower frequency approximation, these oscillations would be even larger, even though they wouldn't be as rapid. And exactly why numerical methods such as the one you developed in your thesis for discontinuous coefficients is necessary, because there's no Gibbs phenomenon. Okay. So, let's see. Okay. So what happens is, and I'll say more about this as we get to the next section, the series converges to f of x if f is continuous at x. Or I should say its periodic extension is continuous at that point. Otherwise, it converges to 1/2 the left-hand limit of f and the right-hand limit of f. If it's discontinuous. So what's happening here, from the left side, the function is approaching pi. From the right side, it's approaching minus pi. So the series will converge, in this case, to 0, the average of the two. Okay, so, and at any other point, like these, even as we go right up to discontinuity, if allowed to continue, the series will eventually converge to the correct value. Just that when you have discontinuity, you got to converge to something. You have no function value to converge to, so it just goes to the average. Okay. So that's all I have about orthonormal expansions. Starting Wednesday, we'll get into the same material for specifically Sturm-Liouville problems and their eigenfunctions. So those will become our orthogonal basis functions, and we'll learn about all the nice properties that they have that will help us solve PDEs. Okay. Oh, only 2 minutes over.